Hello, everyone. As usual, we'll wait another 5 minutes until 1:10, and then we'll start. If there are any questions before that, please post them in the chat. Okay, guys, let's start. As usual, request for everyone, if you can turn on your cameras, that would be great. Thank you, guys. And yeah, since this is relatively small, class, so if you had questions during the lecture, you can always either raise your hands or just raise your voice and just ask. You don't need to use necessarily only chat. If there is something that is not urgent, you can post things in the chat. Okay. Okay, so let's start. So today we're going to talk about several interesting topics, and we'll start with loop invariant code motion. That's going to be the big talk for the first part of the lecture. And then we're going to talk about strength reduction and partial redundance elimination. So some of the more advanced form of the reduction removal. That should give you a flavor of how things can get gradually more complicated. So hopefully you see it's still tractable, but it's getting more and more complicated as we build on the concepts that we learn in this class. Yeah, so there would be things today that you probably should pay like a lot of focus. For example, loop invariant code motion is something you have to implement. So you probably should pay a lot of attention to that. That's going to be part of your assignment 3, right? And other topics would be more like, it would be nice to learn so you get a flavor of the complexity. So I'm not going to spend as much time on that because this is more advanced and more complicated topic. I'll just give you some glimpse of it. Okay, so a few basic announcements. So assignment 2 should be out today. So either Bojan already released it or it should be released soon, right? Then there is a midterm that's planned on March 1st. I don't plan to have any special session for midterm. It's going to be just during the class, right? Okay. And there is a holiday next week, so we're not going to have a class next Monday. Are there any questions about anything? That midterm is going to cover everything we learned until midterm, right? So all those topics will be there. We're probably going to aim for something around up to 90 minutes. Midterm maybe shorter. We'll see. I don't like very long midterms, so. And neither exams, so I prefer them to be, decent size, but not where it's like, a game of attrition and you're just trying to survive, the exam itself. Any questions about assignment, midterm, anything in general?
Do we have any practice midterms to work on, or like past midterms?
I don't think we had any practice ones, but essentially the best, to be honest, what the practice should be more or less is what you get in your assignments, right? So the theoretical problems in the assignments are representative of the midterms, right? And pretty much you can think about whatever I cover in the lectures and give examples. Those problems can be part of your midterm, right? So the midterm is, as usual, is going to have some simple questions, right? That you just, multiple choice type of questions, right? And a few real problems. And the real problems would be like, say, write the equations for the data flow, but for a new data flow problem, right? Based on some inputs, or apply that data flow analysis to this graph, or apply these optimizations based on the description. So no surprises. You're going to see whatever you've seen in the classes, right?
And everything will be on Quarkus?
On Quarkus, you're absolutely correct. We're going to do it online on Quarkus. Most probably it's going to be, again, my personal preference is trust students. So we're not going to do this, fancy, stuff like hands off your computers, don't move and things like that. So, but what we're going to do variation of the questions. So it means that some of you you're going to get the same complexity problems, but they might slightly different, right? So that kind of kills, and it's tight on time. So there is no need to, to talk to others because they would be busy with somewhat similar but different problems, right? So this is my way of handling, fairness in the exams.
Thank you.
Any questions here? Yeah. Okay, so let's move on. We'll just start with the usual thing. Remember loop invariant code motion. So we're going to deal with loops. So all types of loops, because we know how now to deal with do, while, go to, for loops, or any other loops in general. So just remind you that not every cycle is a loop, right? That's an important to distinguish, and we covered this for a long time. We know that the loops satisfy certain properties, like the dominance is among them. And we know how to build loops, and we know what the natural loops are. We know that they had headers. Headers dominates all nodes in the loop. And there is a back edge whose head dominates its tail. So that's essentially what we treat as a natural loop. And for loop invariant code motion, you should assume that this is given to you, right? Someone will already apply this algorithm, giving you a loop structure of the whole program, and you're going to just apply your transformation for that. Right? And we had an algorithm. By now, you should be able to find natural loops. So as one of the potential questions in the midterm is given a control flow graph, right? And instructions in those basic blocks, you should find loops, right? So that's one of the examples. And you would remember when you show it, you don't just say this is a loop, you actually show how you do it, right? All these 3 steps. Dominator tree, right? You do step by step. You do dominator relationship in a full graph, identify back edges, and then you find what forms the natural loop after that, which is very straightforward, right? The thing is, remember that in general, like applying some of these algorithms on really large graph might be non-trivial, but again, you're not going to give in crazy graphs, right? So the dominator tree not going to be too difficult to identify, right? So as soon as you understand what it is and you apply the reasonable algorithm to it, you should find it relatively quickly. Okay, so it shouldn't be that time consuming. Now this is just coming back to one of the Frank's questions, what can be on the exam. But this is a solid question for the exam. Or say, find a control flow graph based on the instruction sequence, right? So pretty much everything we did in different lectures where I pay attention to it, right, and did it formally with you with the examples, it can be on the midterm. Okay, there are the 2 loops can either, if they don't have the same header, they either disjoint or one is nested in the other ones, right? And this is the inner loops. And what's really important for today's lecture is the notion of header and pre-header. So those are specifically done for optimizations like loop invariant code motions. Those are really critical to have. Okay. So I hope by now I repeated, like loops is a very important topic. So I hope you know how to find loops and distinguish one from just cycles. Let's go to a really new content for today's lecture. So loop invariant computation and code motion. So I guess the first question to everyone, why do we specifically care about invariance in the loops and not in other places? So like, why do I have like a whole lecture dedicated for loop invariant code motion? Any ideas? Why is it important? Why not say just in regular functions?
Because if something's not changing, you could just remove it.
Yeah, you're right. But the question is more like, if it's an invariant, why specifically focus on loops? Why not just everywhere in the code? You see the question, right? So there is a difference. It's invariant is always nice to remove, but we specifically study in loops.
If it's not changing, we don't need to compute it at every iteration. We could just do it in the pre-header.
Yeah, Frank, you're absolutely correct. But you're trying, what you're trying to say is why loop invariant is useful, right? That's the question you're trying to answer. And my question is slightly different. My question is, why do we specifically focus on the loops, but not everywhere else in a random piece of code? Because invariance might be outside of the loops, right? Just you had a function, and within that function, there's a plain text. So the main reason is because the importance of the loops, right? So the function might be also called multiple times, right? But proving invariance across the function calls, for example, without inlining might be very tricky, right? You're not going to see invariances easily. So it's essentially the best way to think about it is a super important case, and it's a relatively straightforward. So if you're going to see, say, a function f and some invariant there, how do you know it's invariant, right? You actually need to see that if you call it multiple times, these things might be the same every single time, right? But you're not going to do this for every function because you might have millions of functions and not of them are all equally important. So without some extra optimizations first, you want to find whether those functions are useful, and what to get to that, you really need to apply some optimization, say inlining, where you inline the body of the function somewhere. And what it boils down to, they're only important when they're inside the loop, one of the hot loops. So it's really only important when in the loop. So it turns out the invariants only matters in the loop, and you need to get them into the loop one way or another first, and then you can apply what you learn, right? Okay. So essentially the importance of the loops and the fact that they're relatively straightforward to deal with make them a target of this optimization. In fact, you're going to see if you open a compiler, you're going to see a lot of optimization specifically targeting loops, right? Because of their importance. Okay. So what is the loop invariant computation? Essentially a computation whose values do not change as long as control stays within a loop, right? So as soon as within this piece of code, and you see why it's an important, so it's the definition is tied to the loop itself. And again, as I said, it's specifically this piece of code matters. You could have defined that has nothing to do with the loop, but as I said, loop has it's important enough and has reasonably simple structure that it's both interesting to study and not too difficult, right? So because other things like interprocedural analysis might be too difficult. Okay, so if we find something is invariant, this by itself doesn't really help, right? Because what we really want to do, we want to move out that statement, as Frank just said, to something like a pre-header of the loop, right? Remember, we just, several times I repeated that we have these pre-headers, right? Specifically, so they're built to help with optimizations, right? So there would be a place where those invariants can reside, execute only once, right? And not being executed all the time. The important thing to see is that the fact that something is an invariant doesn't mean it can be easily moved. And you're going to see this. We're going to spend a lot of time today to showing how things can be, ease out and optimize, but not everything. Just because something is invariant doesn't make it movable. You're going to see this. Okay, so let's look at this very simple hammock with their, back edge. So this is as simple as it can be to be interesting. And so the question we have here is whether something is, an invariant or not. So I think I gave you one answer already, right? If you look at an expression b plus c, both b and c are defined outside of the loop, right? They're essentially b plus c is computed once in one branch, and it is an invariant. Do you see any other invariants here? That's a question to you guys. Any other invariants? Like everyone agrees that b plus c is an invariant here. I was hoping that's easy. So anyone has any concerns about why I say that b plus c is an invariant? It doesn't change, right, in the loop. As soon as it's computed, it's the same, right? And nothing in the loop changed the values in b and c. But how about other instructions? Are there any other invariants? How about the second instruction, f equals a plus 2? Is it an invariant or it's not? So I have someone says it is. Can you justify your opinion, Jean-Yan? You can speak if you want.
I think if A is an invariant, then that makes F an invariant too, because it doesn't change.
That's correct. So there's no like anything complicated here. It doesn't change. There would be some complications here, but not right now. As an invariant, it is an invariant, right? Because you just take another invariant, add a constant to that, that becomes still is an invariant. Thank you. How about E equals 3? Is this an invariant or not? So the second one is set as function of a loop invariant. So it becomes a loop invariant itself. How about E equals 3? Any opinions?
Yes, because there's no other values that should be
It's a constant.
studying.
I'm just showing a different example. How about the last thing? D equals A plus 1. I try to have as simple as an example, but to show all different possibilities. It looks very similar to F, right? But there is some difference.
I think it's no, because there could be like if you take the right path, then the value of A it's not the same as like an invariant before.
Absolutely correct. There's one definition for A that is a part of D inside the loop and one is outside. So there's no guarantee it's going to be the same, right? Because we don't know what happens in the branch, right? So you get a feeling now what can be an invariant, what is not. So before we want to move something, we need to find those invariants. So some observations. So what are the loop invariants? The loop invariant, just based on the example we just see, it's when operands are defined outside loop or are invariants themselves. So that's relatively simple, right? So it's either you're fully defined outside of the loop, or you just depend on the constant, which is you don't depend on anything at all, or you depend on the another invariant that just had one definition. But the question is whether each or any in general of these invariants can be moved out of the loop. The problem is that not all loop invariant instructions can be moved to the preheader, and we're going to see now why. So what we need to do, we need to find all the invariant expressions more formally. We are going to define now conditions for code motion when they can be safely moved, and we're going to perform the transformation itself. So that's what I'm going to show you. Okay, so how do we detect the loop invariant computation? That's by far the easiest part. So what you do, you compute reaching definitions, right? There is a reason why we were doing all this data flow analysis. So we start with reaching definitions. Reaching definition tells us what the definition reaches, that statement. We mark invariant if all the definitions of B and C that reach statement A, say B plus C, and plus as an example here, there can be any operation here, right? Minus, division, doesn't matter, outside of the loop. So if both B and C are defined outside of the loop, that's definitely an invariant, very straightforward. How about if one of the B and C are constants? Would it be still invariant or not? If I get something like B plus 2, would it be, and B is defined outside of the loop, would be B plus 2 is an invariant? Guys, it's a simple question. So,
Yes.
Yeah, so I'm just waiting for someone to respond. Please do so. It's just I'm asking more to make sure you don't fall asleep during the lunchtime. Okay, so b plus 2 or like two constants would be obviously invariant themselves. Then what we do, repeat the process. We mark invariant if all reaching definitions of b outside of the loop, or there is exactly one reaching definitions for b and it is from a loop invariant statement inside the loop itself, or similarly for C, the constant's also fine. Until there are no changes in the loop after we process everything, we're done. So essentially, it's either you're an invariant by the first step definitions, or if you get exactly one reaching definition for B, and it is from a loop invariant statement inside the loop, right? So for example, because there might be the case that you are dependent on other invariants, but there are, there's some overrides or some redefinitions here, right? So that's not allowed. But if you're directly dependent, as remember in the example I showed before, from another invariant, that's also safe, right? So that's it, and this is very easy algorithm to converge. Okay, let's look at this example. So what we want to show here is what is a loop invariant and what is not. So let's look at the first statement, A equals B plus C. So anyone thinks is an invariant or not. You assume there is an edge here for the pre-header, right, coming. So just was lazy to plot it. Any opinions? Like A equals B plus C, invariant? Guys?
So B plus C is an invariant?
Yeah, so B plus C is invariant because all reaching definitions of B and C outside of the loop. The constants, I hope, are trivial, right? Nobody's going to ask why this is an invariant and why this is an invariant, right? This is statement by definition is an invariant. Then here there is a convergent thing, and then you see A plus 1 here. That might look tricky because there are different paths. But because we look at reaching definitions, the only reaching definitions tells us that it is this. And it's from loop invariant statement itself that's defined within the loop. And there is no other reaching definition from outside of the loop or in the loop itself. So this is an invariant. But this guy, E plus 2, is not an invariant. And I think it's obvious why, because there's one reaching definition here and another reaching definition here. And you see, you cannot just be naively saying, well, this is invariant and this is invariant, both of them reaching this point, so this is an invariant as well. No, this is two different invariants. They're two different definitions, right? So because of that, that's not an invariant themselves. Okay, I'm guys spending so much time there because you have to implement that code. So I'm making sure that everyone is clear on every little aspects, right? So that you can actually write the code afterwards. So it might sound simple, but we need to go carefully. And I go over other parts a little bit faster. Questions?
Yes. So I don't understand, why do you mark E as an invariant?
Remember our definition. So something that doesn't change in the loop is invariant. So the statement itself doesn't change ever. So something like a statement that something is assigned a constant to something is an invariant, right? What you're confusing is invariant with the variable to having one definition, and it's not the same thing. So E has a name, right? And because of that, you think about it as being two different things, but it's not. It's two different things. So E, if you use the same register, virtual registers, has two different definitions at certain points, but within the definition of itself, it's fine. Yeah. And as Albert said, it's a good point. Like what we are marking really, we're trying to mark the expressions as redundant, right? So 2 and 3 are really the invariants, right? Or B plus C is invariant, right? And then the def of it is it affects as what else we can say about it, but really we're looking at the right-hand side, right? For the invariant itself.
Thank you very much.
Okay, So that's relatively straightforward. I don't think you're going to have issues with what is this. I show you all the typical examples. The question is when we can move it. So for movement, there are several different aspects. First of all, the correctness. Obviously, the movement does not change semantics of a program. I can't just move the code and then figure out that actually not correct in some corner cases. That's not what we want. So correctness is the main concern. For example, if I had something like a b plus c here, can I just move it out here to the pre-header or not, and on which conditions? Another thing is the code shouldn't slow down. So if we move things, the optimized code should be better than the original one. Usually it's relatively straightforward, but it's always there, the thing to check. So correctness and performance are important. Why I bring this up? In the cases we're going to handle in the first part of the class, it's always like faster, right? Pretty much, or not worse strictly. But in the second part of the class, we're going to look at the partial redundancy elimination. And there, if you're just going to all, move things out without control and analysis, you may make things worse. You're going to remove redundancies, but it's only partial, and you're going to add things here and there. It might get worse. So remember, first correctness is the first concern. The second one is performance. So what is the basic idea behind conditions for the code motions? It should define once and for all. If that conditions is true, then we can move it. So what does it mean to define once? To define once, it means that this code should dominate all exits, right? Because what's important, what exit out of the loop, we need to make sure when we move something out, it dominates it. You see here, A equals BC defined in the middle. There's one exit from the loop, another exit from the loop. If I just move these things out, I need to make sure that B plus C was even expected at that output. So it didn't actually add something in the code that was not supposed to ever execute it on this path, right? So that's an important thing. So visibility shouldn't change, right? It should be equivalent. So essentially code dominates all exits. So the things we learn about domination would be useful once again. Then for all means there's no other definitions, right? So there are no other definitions other than that invariant, so we can move it, right? So even if it's invariant, I cannot just move it just because of that. I need to make sure that's the only one. And there should be no other uses. So essentially, we need to dominate all uses, or there are no other reaching definitions to this use, right? So we need to be careful not only with you, and that's what complication is coming from, but also who else is using your value, because out of a sudden I move the value and there are dependent instructions, right, that uses this value. So I need to make sure that the dominance for them is preserved. Okay. So essentially in these code examples, because I want to just describe, it's actually not safe to move it because we moved it past the exit. It was not dominating before, right? So that code was never executed on this path and now it is, and it doesn't mean correctness. Nothing might break, but it's not safe, right? In some cases, you can speculatively do things like that, but that's not, equivalent. And for example, if you had code like that, then, for example, if you had E equals A and A equals B plus C, so the B plus C might be an invariant itself, but it doesn't dominate its use, right? You see what's happening here, right? B plus C, B defined outside, C defined outside. So this is an invariant. But if you look, there is an edge here. So this A comes into here, into E, but it also comes through here, right? So there are two possible values. So that thing doesn't dominate. If I move it out, I would make this dominating this instruction, and before it didn't. So I cannot change the domination property for the users, right? And this one can be moved, obviously, because it's not a loop invariant. So, okay. And it's not a loop invariant because there is one definition inside the loop and one outside of the loop. Okay. So you see things now a little bit more tricky, right? So it looks like, well, that could be an invariant. It is an invariant, but it's not movable in the situation that we see in the loop. Okay, so what are exactly the algorithm now? So you pretty much already see what we need to know. We need to compute the reaching definitions, right? Because the reaching definitions are the key part to figure out what's reaching which point. Then we compute loop invariant computation, right? We compute what's invariant versus not, the algorithm I described a few slides ago. And then we compute dominators, as usual, right? In practice, when I say compute dominators, yes, you would have to do it on the piece of paper. In the compiler, the dominator tree will be given to you. That's already computed, right? So it's not a big deal. And you can find the exits of the loop. So that's also straightforward. That's the node with successor outside of the loop, right? The loop exits. That's easy. You can do it yourself. And essentially, the candidate statement for the cope motion is first is a loop invariant. Obviously, we're not moving non-loop invariants right here. Then blocks should dominate. It should be in the blocks that dominate all exits of the loop. So if it's somewhere in the middle and there's an early exit, I cannot move it to the pre-header, right? So you might be a perfect invariant, but if you're not in the blocks that dominate all the exits, you cannot be moved, right, by default. You also should assign to a variable not assigned to elsewhere in the loop. This is once. Remember, there's once and for all, and this is that once aspect, right? So there should be no other definitions in the loop. And if you only can be in blocks that dominate all blocks in the loop that use the variables assigned, right? So we shouldn't break anything for the uses. The uses should have the same dominance as before, okay? So we only can move invariants from the blocks that dominate all blocks in the loop that use the variable. So essentially, if I had a candidate, I'm looking at the candidate itself, but also at its block, and I found all its uses, right? Through the because I see the reaching definitions, and then when I'm going to look at the uses, I say, oh, if you dominate me, then when I move you to the pre-header, remember pre-header dominates the whole loop, right? I shouldn't change the dominance for the users, right? They should see what they've seen before reaching them, right? Nothing else. Any questions? So it's a little bit more complicated, but hopefully not too complicated. Every step here makes sense, right? So you see how seem to be a very simple concept of invariant to be applied actually is not as simple anymore. And that's why, junior students, when they try to optimize their code, they sometimes move out things they believe in invariants and they get into trouble, right? Because certain things are not actually, it's an invariant, right? But it's not safe to move, right? So this is kind of an example why it is. Any questions? Hope I'm not too fast. Okay. So, and then we perform a depth-first search of the blocks and move candidate to the pre-header if all the invariant operations it depend upon have been moved. So remember, there is a dependency here. If you depending on the two other invariants and both of them are moved, well, you can be moved as well, right? So you might be a valid. So you might become a movable operation. Okay, let's practice to make it, our knowledge perfect. So let's look at the first examples. Please tell me what you think can be moved, right? What is movable? So not just an invariant, but a movable invariant for the first loop. Again, forgive my laziness, there's an input edge in all cases, right? So you can. Okay, first case should be easy. Any answers? So what can be moved to the pre-header? So someone says A and E. So the correct answer is E alone, only E. So anyone can tell me why A cannot be moved? You guys see the problem? What happens if I move A?
Is it because that you could, at the first iteration, you could go to the right path and then compute D again?
Yeah, and in the terminology that I defined, when I move something, that block should be dominating all my uses, the blocks with my uses. So this is a def, right? right? That B plus C defines A, right? And now it affects this, and this guy is not dominated by this block. When I move it out, I make it dominate, right? Remember, pre-header dominates the whole loop, right? So out of a sudden, I change the reachability of the definitions, and that's not correct. Is it clear for everyone? That's important, right? Yes, you're going to implement this. So I understand that for some of you it might sound trivial, but I want to make sure no one makes those mistakes, okay? You see why those conditions are important. So the last condition here was not true. Let's do the second loop. Ronyan, do you see why E is fine, but A is not fine?
Oh yeah, I got it.
Okay. How about the second case, guys? I promise that the second part would be faster, but this is a very important thing you're going to implement that I need to make sure that everyone understands it. Someone's asked where are the exits. There might be no exits, Albert. It's like an infinite loop, right? So why not? Actually, from a compiler perspective, an infinite loop is a perfectly legitimate loop, right? So they can give it. Like, it's suspicious, but you can't just remove those. In fact, I've seen examples when I work on the compiling real industry compilers and seen people had infinite loops for like delays for something. So there was something external that couldn't stop like a process, right? So you cannot, if you just go and see someone's infinite loop and remove it because it's redundant, you might disappoint the original programmer by expecting the certain delays. Okay, guys, I'll push you a little bit. A equals B plus C. Is it an invariant or not? First question. And the second one, can it be moved out or not? You already know what's the invariance here. We answered that question before. What's movable?
I think it's movable.
A equals B plus C is movable. Any other opinions?
If there's no exit, then how can they dominate the exits?
Well, if there are no exit and the exit is an empty set, then it dominates all the exits, right? I know it sounds funny, but it is. If it's an empty set, then it satisfies the property, right? You just you scratch that from your conditions, right? There's no exits. Okay, I'll help you a little bit. So A equals B plus C is an invariant, right? It satisfies all the properties. There's no exits here. So, and it's the sole, definitions here, right? And more importantly, it doesn't break anything for this guy. That's what's important, because you see it's not as trivial. There is an A here, there's a hammock here. But if you look at the reaching definition, this is the only reaching definition. And this block dominates this block, right? Everyone sees this, right? There's a dominance between these two blocks. And that means this can be safely moved out. Then, after this is moved out, then this guy doesn't have any other definitions within this block, and that's an invariant. So this guy can move out, right, as an invariant as well. And because D is not used anywhere in this block, there's no problem of moving it out. So both these statements can be moved out into the preheader. E2 and E3 are invariants, but neither can be moved out because of this use, right? If there won't be a use of E, they could be moved out as well, out of the loop, okay? Okay, hopefully it helps. So you got by now, hopefully, how the more standard things work. But there are definitely situations where you cannot prove, but you want to gamble. So you want to do something speculative. For example, there can be situations then most loops are executed, right? Typically, right? So we can relax certain constraints on dominating exit. So that's the question we need to answer. what we can do, we can relax that domination of the exit if destination not light after loop. So for example, if I write into something, right, a variable, and I cannot prove that it's not dominating. You see D is here and the exit is here, but that D is not needed ever after the exit, I can still move it out, right? So that's one way to relax the conditions on dominance, because it's quite, unfair. Like it happens to be a complete perfect invariant that can be moved out, and there is some side exit that might have nothing to do with this variable D, right? And now I prevent D from moving because of this side exit. And that might be like an error handler or something, who knows, right? Has nothing to do with these variables. So this is not a reason, so that can be relaxed. And in other reasons, you can compute something in the pre-header without causing an exception. So if the statement you deal here actually doesn't cause in any violations, like you cannot do division, because if division is divided by 0, then you get an exception or something else, or either right, that can cause some exception. But even an instruction that doesn't cause an exception itself, then you can compute it in pre-header. You're actually going to change the dominance, but you don't really change the program semantics, right? So this is the way that you can go a little bit more aggressive. Another transformation that we suggest you can implement is called landing paths. So essentially, you just put a predicate around the loop, and then in the loop, when you're there, it's executed at least once, right? The predicate is true. And then you don't need to worry about the situation where you enter the loop and exit it immediately and never executed the full iteration of the loop, right? So this is essentially the special case that we had to handle, and it might be like, it would be easier just to check it once outside of the loop, and then you can do way more optimizations. That's called landing paths optimizations. It shows pre-header executes only if enter the loop, right? Okay, so this is essentially avoids this. What if I reach this way or that way? You always know that pre-header is executed only the loop is true, right? The condition of the loop is true. Okay, so hopefully I show you what it is. I really go into a lot of details here. We cover the precise definition and algorithm for loop invariant code computation. We look at the algorithm for code motions, and we look at the conditions and how they can be slightly relaxed. And you probably noticed we again use reaching definitions and dominators in optimization. So hopefully you see where while force you to learn all of that, like it's keep coming and coming and again, right? Those concepts will be useful, right? Okay. So we covered that. Let's start the second part, induction, variables, and strength reduction. So we start with briefly overviewing these optimizations, and then we go over the algorithm to find induction variables. So everyone probably intuitively know what the induction variable is, similarly to what the loop is. A lot of things I'm talking about you faced before, but we're going to do this formally again. So this is the original loop written in a language like a Fortran-like. The for loop that goes, and assign values of the array into zeros. This is how it's going to look like after the code is generated. Remember there, if you took any other compiler classes that focus on the front end, you would know that the code is generated line by line, right? Pretty much. So you see the instruction, you generate the equivalent code. When you see it, it looks for humans extremely suboptimal, but that is what compiler does, right? The optimizer is supposed to fix it. So what you're going to get here is something like that in the pseudo LLVM-like code. If statement, some computation of the parameters for the loop access, then the loop access itself, induction variables, that's the guy here, and the goto, right? So what I'm going to do now, I'm show you some definitions. I'm show you what they really represent in the real code. Okay, so this is a really tiny loop here. So basic induction variable is essentially something you wouldn't be surprised with. It's a variable who has just one definition in the loop of the form x equals x plus c or minus c, where c is a constant, right? Or a loop invariant variable, right? Something that doesn't really change. Constant loop invariant variable doesn't really makes it different from the loop's perspective, right? So essentially, it's a basic induction variable because first of all, it's an induction variable. Its sole purpose is to just update where I am in the loop, right, and nothing else. And it's basic because it really doesn't depend on anything else, right? But there are other induction variables, not basic. We just call them induction variables. And there are like induction variables, whether it's a basic induction variable or with this form, or if it's a variable that defined once within the loop, whose value is a linear function of some basic variable at the time of the definition. So essentially, if you had I equals a plus 1, it's an induction variable, but then you had something like 4 multiplied by I, that's also induction variable, just not basic. It's just an induction variable that's dependent on the basic one, right? So any linear combination, right, would make that an induction variable. And soon you'll see why that's useful, right? Because we can actually do some optimization with it. So there's the basic ones that's just plus minus constant. And there's the one that's a regular induction variable that's a linear combination with constant factors. And essentially these linear combinations from the same basic variable, they call the family of a basic induction variable B. So essentially it's a set of induction variables such that each time A is assigned in the loop, the value of A is a linear function of B, right? So essentially if, as you can see here, the T1 is just all the time, it's only had one assignment, and this assumption is linear combination of Y, it makes it a family of I, right? So we get basic and it has a family, like everything that depends on it, right? So that's pretty much the key definitions here. And why the hell we care about that? So strength reduction. So if A is an induction variable in family of basic block of this form, we can simplify those expressions. Remember, those expressions has multiplications and addition, right? And we can make it a bit simpler. So we create a new variable for each of these induction variables, and we do initialization for them in the pre-header, and then we track the value of B, and everywhere we see something like B equals B plus X, we add this, right, for our new variable A prime, and then we replace the sole assignment of A with A equals A prime. So how that would help? Well, as you're gonna see that we moved most of the actual complexity outside of the loop, right? So for example, before, I would have two operations that deal with the induction variables. There was one, T1 equals 4 multiplied by I, right? And there was T2 that was doing address of A, which is expensive operation, as you can imagine, plus T1. And that is a constant, right? Because the loop is constant location in memory. So what we're gonna do here, we're gonna think about there's a borders here. So we're gonna move this stuff into the pre-header, and everything here would just becomes a simple add plus 4, right? Constants. So instead of having multiplication and address taken at each iteration, we got rid of those two induction variables, okay? What we do next? So after that's done, you see the code doesn't look fully optimal yet, right? We can look at it and see, you know what, certain things are not really needed. Like look at this guy, like T1 equals T1 prime, and there's this T1 prime change that does really need some things that might turns out that I don't. So we need to do copy propagation and that code elimination, right? And then we would optimize basic induction variables so that we can eliminate anything else that's used only for computing other induction variables and loop tests, right? So a lot of that can be removed. So the way we do it, we find the induction variable that belongs to a family of B, something like this, simple test like that, and we replace the comparisons like that with something like that. Why is that important? Is because that would allow us to either fully get rid of them and keep them all in a simpler form when we compute it, right? So that would make a lot of the cases simpler. And this is an example, and I think we pretty much did most of it already. You've seen how I can get rid of these two things. So the first step would be essentially I get this piece of code, right? When I go from here to here, I get two new variables, T1 prime and T2 prime, right? and T1, T2, just reuse them, and this is the addition. And what happens next, right, is that I look at what's useful versus what's not useful. So for example, I found that T1 is, I can copy propagate it first of all, and then it's really not needed anywhere, right? It's not utilized anywhere. So there is no reason to keep it, right? It can just go away. And then T2 is needed because I was using T2 here, right? But I can get rid of this statement because T2 itself doesn't use it anymore. So I just need T2 prime, and this addition can go away. So the only thing that has to stay is this store, right? And that addition. And the conditions will also simplify because now I have, T2 and T3 computed. So that's the only thing I need to compare. So you see, I get this T3 here. That is A plus 400, right? I just did, convert this statement to this statement with all the constant. So I move out that extra, constant compute from here into here. And then my constant becomes just a variables, right? So there's no like extra addition here needed anymore, or address taken. You see, this is removed and this plus is removed, right, from the condition. So everything that's complex, move out of the loop, right? Like keep the loop as simple as possible. Reduce the complexity of every operation. That's the goal. So you see, at the end of the day, I just had one store and one induction, right? That's it. Nothing else from this loop. Everything else was removed. So this is what the codegen generates, and that's what I get at the end. And what's important is that the loop really had just this thing and a very simple test, right? So the test doesn't look like that, because if I just go from here to here, I simplify, but the test becomes complex. So I need to make the test simpler as well for the condition. Any questions? So you see, right? We look at the basic induction variable. That's very intuitive, right? Something that just has something like I plus 1 type of form, plus minus. And we find out the family, something that is a linear combination of it. And then they all can be nicely replaced with the formal definitions with the new variables. And then we do copy propagation, right? We propagate all the values. They all, straightforward here. And we remove the dead code, anything that's not used. Dead code elimination is trivial here because it means you don't have any uses, right? If you look at your reaching definitions, if there's no uses, it means it can be dead code eliminated. And that's it. And then the last step, you replace the conditionals of the branches. Any questions here? Okay, if there are no questions, then I think we will stop here and we'll continue into basic induction variables and optimization associated with it in the next hour. See you in 10 minutes. Okay, let's come back. Okay, so we've seen how, detecting basic induction variables and their families can help optimize the code quite significantly. Let's build on that and see what can be done and what cannot, and what are the limitations right now. So algorithm for detecting induction variables is relatively straightforward, right? You can easily find induction variables like I and K, because you just look at how they change. So here I is changed only here, and K is changed in multiple places, but it always has this form, right? So one thing I want to highlight, that the fact that it changed in different and the different branches doesn't make it by itself a not basic induction variable. Okay, you might have multiple different assignments. So I and K are both induction variables. You just always look at the definition. Then how about the families? So the families for K is the variable m. It belongs to its family because its m is simply defined as 2 multiplied by k, right? So it essentially has one coefficient being 2 and another one being 0. So how are we going to implement the strength reduction algorithm? The key idea is for each induction variable A, which is C1 multiplied by B plus C2 at the time of definition, we had a variable A prime that holds expression like this at all times. And we then replace the definition of A with A equals A prime only when it's executed. So the result is the program is correct, and definition of A does not need to refer to B anymore, so that you can do different type of optimizations like dead code elimination, right? So how do we find induction variable families? So let's say B is a basic induction variable. And so what we want to do, we want to find all induction variables A in a family of B. So something like that, where B refers to the value of B at the time of definitions, right? So this is the family of B, right? So what conditions are is, first, we want to have A has a single assignment in the loop of this form, like B multiplied by C, or the other way around, or division, and all these different things, right? So essentially, we want manipulation that is manipulating this with a constant, right? That it's keep the linear property. So multiplying by a constant, adding a constant, changing the sign, this is all satisfies the property. So this is one condition. And another condition is where you kind of iteratively depend on something else that is an induction variable. So D is an induction variable in the family of B if it has a single assignment of the same form as before, and that there is no definition of D outside of L that reaches the assignment to A, right? So we need to make sure there's no like redefinitions of any kind. And between the lone point of assignment to D and the assignment to A, there are no other definitions of B. So these somewhat maybe cryptic statements just really check that there's no redefinitions, that whatever is an invariant, whatever is an induction variable is not redefined in a weird way so that break the linear relationship between them. So you just really need to make sure that if something else that is dependent on the induction variable stays in its family, it should be of that, of that shape, and there is nothing else that would redefine either D or B, right? Because it belongs to this family. Because if I'm a linear combination of B visually, but there is something that changes B in between, right, the two, then it's not really this linear combination anymore. It's something else, right? So I really just need to prove that if I had this equation is not broken by either redefining B or redefining D somewhere, right? This is an intuitive way to say exactly what's written formally here, right? When I say this, you just make sure that nothing breaks it. Okay, so essentially that leads to these, formal conditions for something to be belonging to the family of an induction variable. Again, here I'm going to spend a little bit less time because that's not something you're going to implement in such details. And I just want to get you a feeling of how the algorithm look like. So essentially there are two conditions. Remember, one condition is a single assignment in the loop. That's the easiest one, right? If there's only a single assignment like that in the loop of that linear combination, then we're done, right? For example, in this loop, I is a basic induction variable, right? Hopefully no one has the questions about it. Is there's I equals I plus 1, right? And the variable T1 that has just a single assignment of this form, 4 multiplied by I, is just belongs to the family of I based on this rule C1. It's a very simple rule, right? If you had only one assignment, right, then that's it, right? But then there can be things that are dependent on T1, right? So this is just directly depends on I, right? So this is you check this statement and you're done. And there are the other guys that are dependent on T1. They can also belong to the family, but then they need to satisfy more complicated rules, right? So for them, they need to be of that linear property, but additionally, they had to satisfy those 3 rules. And that's a little bit more complicated. So let me show why that might break. Anyone is with me? Am I too fast? Anyone had any questions here?
So let me assume if you just remove the T2 definition down below T1, then it makes it an induction variable also. Is that true?
What you're saying you would just remove what T2?
Sorry, not remove, just move it down for one line.
Yeah,
T1.
correct. Yeah, that's what makes it different, right? The order, right?
Oh, I see.
That's
okay.
that the order is, again, this is a really small example, and every instruction here in a specific place just to demonstrate how the rules might break, right? So remember, the rule 2 says no definition of C outside L reaches the assignment of A. So the problem is they're linearly, but they're redefined, right? So this is not really as linear as it is because there's this multiplied by I and there's this redefinition in the middle, right? So that redefinition kills it, even though it has the right form, but you shouldn't be fooled by it. That rules requires that it, so no definition outside of L reaches the assignment of A, right? It really says it should be this equation and nothing else is redefined, neither DOB, right? That's what we're trying to check, right? So we don't want to be too restrictive. We won't just say this alone. We want the dependent instructions allowed to be also part in the induction variable, but only if they satisfy this property. But then for T3, which is actually not that different from the algorithm perspective, plus constant or multiplied by a constant is the same thing. But the place where they're located matters, right? This thing satisfies all the property. So condition 2, it has all the right thing. It has A equals to T3, D equals to T1, right? So this is our, linear thing, right? This is D, and the B is I. This is basic induction variable, and the A here is T3, right? So that's the statement itself. Is this clear? So
I have a question.
Yeah, go ahead.
So if T1 is placed before T2, then would that make T2 a family of I?
Yep. Yeah. So really the difference, like what I'm trying to say, the difference between T2 and T3 is really where they're located with respect to T1.
I see. Thanks.
Right? That's what makes a difference. In one case, they're redefined, in the other case, it's not. Okay. Okay. Here is another example. I just left it to you to play a little bit. And so I give you the answer here, right? So it would be easier for you to self-check, but it's just an example, right? You can go with it yourself and see, it would help you to see whether you understand it or not, right? Okay. So there are answers here, but try to do it yourself and then look at the answers. Okay. Okay. So what we did in the second part of today's lecture, we essentially covered precise definitions of induction variables. We had a systematic identification of them. we show why the hell they need it, strength reduction, right? You see, so we're not just doing this for fun to say, oh, this is an induction variable, this is not. This is not for the sake of definition. It's actually helpful to optimize things. And we show how you do all the cleanup. So you eliminate basic induction variables. For that, you use copy propagation, dead code eliminations. This is easy for you because now you know how to do reaching definitions, right? So you are equipped for doing this type of transformations. You can eliminate things using other induction variables calculations, and you can replace loop tests, right? You notice, right? So we start with a simple loop test, then we do transformation, and it helps, but loop test gets more complicated, right? So to avoid that, we do the extra transformation and clean up the loop test, right? So you've seen, because the first loop test was something like I bigger than blah, and then we do transformation and we get this t variable, but then it compared with a weird constant. And then we move this constant out of the loop, right? So we always compare with something simple. So we never complicate the loop tests. And in general, like everything we do here, it only makes things faster. And to eliminate another induction variables, as I said, we use standard optimizations, that code elimination and copy propagation. Remember, we're using the simple versions of them that shouldn't trick us. There are more sophisticated versions of these optimizations we're going to cover eventually, but in this local case, it's very straightforward. You literally have a constant equals to something, and then there's one use or no uses, right? That's what you deal with. Any questions? Okay, so there is a next part that's called partial redundancy eliminations, which is actually a quite tricky topic. I demonstrated here to show you how certain cases in the loops where we cannot handle can be handled after applying this. And another reason that why I want to show it, remember in the flow analysis so far we had, forward to backward analysis, but I wanted to show it doesn't have to be always only forward to backward. It can be actually bidirectional. So I'm going to show you an example of a flow problem that is more complicated than anything you've seen before. I'll show you it can be bidirectional, but that doesn't mean it won't converge, right? So the fact that it's bidirectional, it means they apply some equations in one direction, some in the other direction, but then it still is the same property of monotonicity and everything else that we learn can still allow you to prove that the algorithms converge in a certain number of steps. The equations won't look easy, I'm promising you, so I'm going to just leave some examples to yourself to study if you want to go deeper into that, but I want to at least give a flavor of that, okay? So essentially this thing, partial redundancy elimination, it doesn't really have anything to do with the loops directly, but it helps loop invariant code motion for the cases where we struggled before, where those conditions, albeit very simple, were restrictive and didn't let us do things we want. So partial redundancy elimination could help in those cases, okay? It can also be extended to do strength reduction, but I'm not going to do this today. Okay, hopefully you would now understand why you're dealing with this relatively complicated part next. So I start with the basic stuff. So common sub-expression, something we've seen before, right? This is a form of removing redundancy. So if I had a plus b here, a plus b here, and a plus b here, occurrence of expression e essentially can be redundant if it's related along this path. So here it's everything is straightforward. A plus b computed here and here. Why do I need it here? It's redundant, right? It's the same a plus b computed. So redundant expressionation can be eliminated. We essentially, the previous case, everything is straightforward. So there's nothing fancy here. We can know how to handle that already with our data flow analysis. Where the complications come is this part, is the so-called partial redundancy elimination. So what if I had that computing here and here, but not here? So essentially that statement is partially redundant, right? So in the sense that it's available on that edge, but not on that edge, right? So it makes it redundant, but only partially redundant. So the formal definition is if it is along one path to P, there's no operand redefined for A and B here, then this expression is partially redundant. Partially redundant expression can be eliminated also if we can insert computations to make it fully redundant. So if for whatever reason I can, satisfying certain conditions, can insert a plus b here, then I can get rid of this here. So why the hell I would ever want to do it? So the question for you there is, why would I want to add something at the top just to remove something at the bottom? What the intuition for this could be? Isn't it the same? I just add one expression and, you know, remove it in one place and add it in the other place. Doesn't really change anything. Any intuition? Why would it be interesting? Anyone with me? So why do you think that trade-off would be ever feasible? Any guesses? Even if you don't know the answer, try to guess at this. Okay, so this is kind of the answers. The answer is that not each path or each blocks are equal, in the sense that there can be some blocks that are within a loop, and the computation there is extremely costly because you might be doing this 1 million times. And on some path that a plus b might not be available, but I would love to move it here, because if I do that, I would do it here, but not here. And this is 1 versus this is million, right? So the fact that I'm moving things between different basic blocks might be actually profitable. So essentially what I really want to do is that I want to just make that available here, and then this expression then can be eliminated, because a plus b is available along this edge, but not along this edge, right? So essentially remaining, and remember when we were dealing with, you know, all these optimizations for the loop, like loop invariant code motions, these things we cannot handle, right? Like that's, strictly speaking, that's not doable, right? Like I was moving something that won't be safe. So I only can do it if I actually inject it here, right? So, so the idea is that you inject that in here potentially, if you can do it safely, and then you remove everything else just by using copy propagation, right? So you define a new variable T10 here, make it a plus b, and then everything becomes T10, and then you propagate the values and everything's, you know, done. So essentially, after that's done, you get something like that. Okay, that's a very high level ideas. You want to understand it. So you would see that in compilers, when you go outside of the basic optimizations, you might do tricks like you make something worse to make something else better, but that something else better is significantly better, right? So there's a trade-off. Before, we're mostly doing something that is just absolutely always better. And that's easy, but remember there are a lot of cases where things are not that easy, okay? So the algorithm for partial redundancy elimination is actually not, as I said, is not really straightforward. I'll just cover as much as I can in today's lecture and then continue maybe in the next lecture if time permits. But essentially the basic idea, I hope you got it. We find that along certain edge that's important, which is like a back edge on the loop, the computation is redundant, but it's not redundant everywhere. So we need to inject those expressions along different other paths to make them redundant artificially. And there are a lot of questions. We'll try to cover some of this today. So the question is, what expression are good candidates for elimination? How to distinguish which expression we should apply this when we shouldn't? How to find candidates? Then safety. Where can we safely insert computations without breaking, you know, the correctness? And the third piece is, where do we want to insert them, the locations? For simplicity, we assume in this lecture, we're going to deal with something like a plus b all the time. But in general, this is done, this is general and can be applied for any expression in parallel, right? Not just this one, right? It has nothing to do with specific of the operator itself. Okay, so the first question, which occurrences we want to handle? in common sub-expression, we deal that something is available along every path. That's the key thing about common sub-expression elimination we did before. If that's true, we can eliminate it fully. In partial redundant, we get E partially available if it's related at least one path with no subsequent operands. If so, it can be eliminated. And essentially that's, definition difference. How we can find partially available expression. So essentially, you can do them more or less the same how we did previously. We do this partially available expression that has their own kill and allocation set. So essentially, there and the input set is defined here, as you see, the regular, forward propagation. So locally available locally available set that we define as AVLOC is essentially the expression that's available downwards. So if we see something like here, but then it's written here that's not, it's not locally available because it becomes, it's killed, right? So expression is killed if there are any assignments to its operand, right? So we want this, expression that's locally available, but we also need to remove everything that was killed moving downwards. Okay. So here, for example, it's available, here it's killed. Right? So this is still more or less the same that we've seen before. I'm not going to spend too much time here, but seeing this is not dramatically different from the precise expressions. Here, I leave that example to do it for yourself because this is a really trivial piece of code. You can assign this in and out sets yourself. Here, I just give you what is kill and what is alloc for each expression. And surprise, surprise, we're going to find that there is one expression here that is partially redundant, A plus B, right? So there's no surprise here. It's a really simple piece of code. So that kind of tells you how to find them, right? You just really find the expression along one line, and then you just, add it to the list of the candidates. So that's more or less straightforward. That's a traditional forward pass. Then there is a safety issue. We want to never introduce a new expression along any new path. So if it would be just this, that would be simple, but you might have something like that, right? So if I bring up this thing, I'm introducing something on the path it never seen it before, right? So I need to make sure that I would never inject it on the path that we've never seen before. So is everyone with me? So you see what's happened. If it would be without this branch, that would be adding it here. It means I was already anticipating it here, right? So adding it here wouldn't be a surprise for this basic block. It shouldn't generate an exception. But this might be a completely new path. And now out of sudden, this expression exists here. So God knows that what it leads to, right? So we need to be safe about that. So it is unsafe to insert A plus B in the general case here, right? So we cannot just add it here because of that complication. So the solution is to inject this expression only when they anticipate it. So what does that mean? It means that, first of all, we're never going to increase the number of computations on any path, because what if we compute it on the path that never happened, and that inside some loop as well? So who knows? We might make it worse than it was before. So under the simple model, we guarantee that the program never got worse. In reality, there might be some, tricky things. So I say it never get worse. It's only with respect to how frequently I do A plus B, but I change other factors in the code that you're not even aware of, something like, say, live ranges of the variable. So by moving something somewhere, I actually make other algorithms like register location now under harsher conditions, because this variable are now, say, live on the longer range of code, and I can easily rename it, for example, right? So remember, just by moving something here and there, it sounds straightforward. I didn't really change anything, but you change something that affects other optimization. So strictly speaking, under simple model, you don't really change anything. It cannot get worse. You only inject it where it was before. but reality, it might get worse, right? There are ways to handle that. I'm not going to cover this today, but just remember the fact that I moved something and it seems that it was anyway executed in this spot doesn't mean everything is equivalent. So first, there is a safety concern, and the second case is the performance concern. There are two concerns when we deal with where to insert. Never insert it where it's unsafe, and try not to get things worse or significantly worse. Okay. Then remember we just had a forward pass. Now we need to deal with anticipated expressions, right? So we want to find the places where expressions are anticipated, right? So we expect them to be. And very similarly to how we did before, we defined a backward flow problem here, right? We had blocks that are locally anticipated if they are upwards exposed. So it's the other way around. Now it's not exposed here if it's not redefined, right? So it's not going to be exposed here, but it's going to be exposed here. So this is essentially something very similar, but just backwards. So you can try it again, and essentially the answer, I'm just telling you, the expression a plus b is going to be anticipated at the end of the first block, and computation may be safely inserted there. So in this case, simple, everything is safe to do, okay? So why is this an important thing to show? Because everything seems like as before. Well, an interesting thing is now we would have to deal with the equations which part of that is forward, part is backwards. And so we want to essentially answer questions, where do we want to insert the computations? And essentially the data flow problem we're gonna define there would actually be both backward and forward. So essentially the answer to this question is going to be a data flow problem that has these two essentially input and outputs. One is placement possible. Input is we want to find placements possible entry of the block or before, and the output is placement possible at the exit of block or before. As this is the problem we try to solve. And after we solved these equations and we found for each expression, we found everything being 1 or 0. And when we found all the solutions of these equations, we insert at the earliest place where placement possible is equals to 1. So that's the place to insert, and only place an end of the blocks. So essentially this is some extra conditions, and we don't want to insert where expression is already available. So remember, we don't want to increase the code. If there is an a plus b available on that branch, we don't want to exclude it. So this condition write down what I said. We only want to inject things that were not already available, right? So this means if it's already available, right? EV out, something we found before, available, partially available expression, then we do negation of that. We don't want to add it there. And we also want to remove all upward exposed computations where that is 1, and that's the condition for it. Again, the cool thing about it, but you can practice it. I'm not going to do it right now because it's a very simple graph. You can just follow their equations. Yes, can you hear me? Or okay. So let me see how I'm doing on time. Okay. So essentially, the output set for the placement possible, we only want to put an output when we only want to put an output for this block only if it's an entry for all the successors. And for the input, we want to place it in the input of this block only if all conditions are true. We have a local computations to place or a placement at the end of this block, which we can move out. And we want to move computation to the output of all predecessors where expression is not already available. And we can gain something by placing it here. So those things are really safety constraints. This is a performance constraint, right? So essentially, I figure out the math on how to move things around, but it's not, might be not always beneficial. So I only want to do it when it's beneficial. One thing, as you can see, because that pass consists of forward and backward component, it's the first time when we see a data flow analysis that would be both forward and backward. So this is a so-called bidirectional problem. But remember, even though it's bidirectional and the lattice is finite, it's just zeros and one, and if we define the transfer functions properly to be monotone, it will still converge. So don't think that because I can go up and down, it doesn't mean I won't converge. No, it's monotone, right? So essentially, I would define my equations, what we had before, right? So it's placement possible would be essentially a backward piece, right? Because I'm going through all the successors. And here I'm going through all the predecessors, but because in the same algorithm I'm going through both the successors and predecessors, right? I'm ending to have a bidirectional problem. So this is anticipated, analysis that we did before, right? We're going to reuse it here. And that's essentially what we're doing here. We're checking that that thing is anticipated and it's not redefined, and there is something to gain from doing all this hacking, right? So there is something that would be useful to do it. So as you can see here, the only reason why I want to show all that complexity here is that you would believe that their data flow analysis can evolve. It's not just all the straightforward forward and backward passes with simple equations. Equations can be quite complicated. They might be bidirectional, and it still converges, and can have proven heuristics for that. And it's important because that placement possible is required for partial redundancy elimination to work, right? And that is required to actually do loop invariant code motions efficient in practice. Because remember, those simple restrictions are too restrictive. They are simple, but they're very harsh. If you just always require that everything dominates the axis, there's a very few things you can move out. But again, if there is that expression is anticipated and or it's not useful, like it's that, we can still avoid these restrictions using these algorithms, and we can still move the invariants out of the loop. Okay, so all that complexity comes back to the loop invariant cone motion, and together with that, it can allow you to move things that otherwise are not movable. Again, here for these very simple examples, I leave you, very simple examples where if you want, you can practice yourself, okay, on the placement possible. And that's just tiny little bit more complicated case. And again, I brought you all the answers for all the intermediate things, so you should be able to do the rest of the equations yourself. Okay, so yeah, so here I've just showed that some, basic, intuition, not a formal proof why it's safe to do it, because we'll only insert when it's anticipated, right? That guarantees that. And performance is also good because we're using heuristics. We never increase the number of computations on any path. But remember, I said this is good, but that might be not enough to negatively affect performance. So this is heuristics. Sometimes it might break. Okay. Okay. I think it was enough. That latter part of the lecture, this is more, to be honest, more like an example, and I want you not afraid to experiment yourself. We cannot go formally with each step here. It's probably going to take another 30 minutes. So if we had time there for the lectures, I might go into this more carefully. But here, I just more for you to get the intuition, right? The fact that something is partially available, it's not hopeless. It can be done, but you need to be really smart about this. All partial or speculative optimizations are very tricky compared to the straightforward common subexpression eliminations, right? But we had the machinery, and you already learned the machinery that can make this happen. Any questions from anyone? But as you probably have seen, I spend more time on the loop invariant code motion, right? And on basic induction variables. It all was kind of, tweak towards what you're going to actually hack. So, and based on the importance, this is more for demonstration. So hopefully there are no questions about loop invariant code motion. That I think I covered very, very slowly. Any questions, guys, about it? Are you still here? Other than Albert? Anyone has any questions? Okay, if there are no questions, that I'll give you back whatever 13 minutes. So that's it for today. And I just remind once again, there is no class next week. So see you in 2 weeks. Thank you, guys.